A long, long time ago, about 4.5 billion years ago to be more exact, something incredible happened. Out of a swirling cloud of gas and dust, a planet began to take shape. That planet was Earth, our home, our blue marble floating in the vastness of space. But how do we even know how old Earth is? It's not like there's a birth certificate hidden somewhere under the crust, right? Scientists have spent decades, even centuries, trying to uncover the story of Earth's origins. Through the fields of geology, biology, astronomy, and environmental science, they've pieced together a timeline of how our planet formed and evolved. Understanding Earth's age isn't just some fun fact to impress your friends. It's the key to unlocking the mysteries of how life began, how continents moved, how oceans formed, and how everything around us came to be. In this video, we're diving into that ancient story. We'll explore how Earth was born, the fascinating scientific methods used to calculate its age, and why that number, 4.5 billion years, is one of the most important numbers in science. The story of Earth's beginning is deeply connected to the birth of the entire solar system. Picture this. About 4.6 billion years ago, there was no sun, no planets, just a vast, silent cloud of gas and dust drifting through space. But then something changed. Maybe it was a nearby supernova, maybe just a natural shift. Whatever it was, that peaceful cloud collapsed under its own gravity. And that's when the magic began. According to the nebular theory, this collapsing cloud, called a nebula, started to spin faster and faster. At the center, most of the material clumped together to ignite what would become our sun. Meanwhile, the leftover dust and gas flattened into a spinning disk around it, known as the protoplanetary disk. From that disk, tiny particles collided and stuck together, slowly building bigger and bigger objects. Over millions of years, these clumps grew into the planets we know today. And one of those planets, born from dust, heat, and chaos, was Earth. Inside that spinning disk of dust and gas, a quiet but powerful process was unfolding, something called accretion. At first, it was almost invisible. Tiny particles of dust and gas bumping into each other, sticking together thanks to simple electrostatic forces. But those little collisions added up. Bit by bit, those clumps grew larger, becoming rocky building blocks known as planetesimals. Think of them as cosmic Lego bricks, drifting through space, crashing together, and forming bigger and bigger chunks. As these planetesimals grew, gravity took over. The more massive they became, the more material they pulled in. Eventually, some of them reached a new level. They became planetary embryos, sort of like teenage planets, not quite grown up, but getting there. These embryos kept swallowing everything in their path: dust, gas, smaller rocks, until one day one of them grew large enough to become what we now call Earth. It was rough, chaotic, and incredibly hot, but it was the beginning of something extraordinary. When Earth was just born, it wasn't the cool blue planet we know today. Nope, its surface was scorching hot. Imagine non-stop collisions with space debris, intense radioactive decay, and crushing gravitational pressure, all of that packed into one fiery ball. This extreme heat melted much of the planet, turning it into a swirling ocean of molten rock. But something important was happening beneath the surface. Heavier elements like iron and nickel started to sink deep down, pulled by gravity toward the center. Meanwhile, lighter elements floated up to form the outer layers, the mantle and the crust. This natural sorting game is called planetary differentiation, and it was the very start of Earth's internal structure, the layers that make our planet so unique. Without this process, Earth wouldn't have a solid core or a protective crust, and life as we know it probably wouldn't exist. In Earth's earliest days, the atmosphere wasn't like the air we breathe now. Instead, it was born from the planet itself. Gases trapped inside were released through countless volcanic eruptions. Imagine massive volcanoes spewing clouds of water vapor, carbon dioxide, and nitrogen into the sky. Slowly but surely, the water vapor began to cool and condense, falling back down as rain. Over millions of years, those rains filled the lowlands, creating the very first oceans. And these oceans? They were more than just vast pools of water. They were the perfect cradle for life to begin, a place where simple molecules could come together and start the incredible journey that would lead to all living things on Earth. Without this watery beginning, Earth's story, and ours, would never have started. Figuring out exactly how old Earth is, that's not as simple as just looking at rocks on the surface. You see, Earth's surface is like a giant recycling machine. Rocks get worn down by wind and rain, pushed deep underground, melted, and formed again. So, the stones we walk on today aren't the original ones from billions of years ago. Because of this, scientists had to get creative. They developed special techniques to peek deeper into time, beyond the surface. One of the most powerful tools is called radiometric dating. Using this method, scientists can measure the tiny clocks ticking inside certain minerals, giving us an accurate age of the oldest rocks, and in turn, revealing Earth's true age. So, how does this radiometric dating actually work? It's all about a cosmic ticking clock hidden inside certain elements. Some elements, like uranium-238, are radioactive. They slowly break down or decay into stable elements, like lead-206. This decay happens at a steady pace, a bit like sand slipping through an hourglass, measured by what scientists call a half-life, the time it takes for half of the radioactive atoms to change. By carefully measuring the ratio between the original radioactive element, the parent, and the stable daughter element it turns into, scientists can figure out how much time has passed since the rock formed. It's like reading Earth's own timekeeper, allowing us to look back billions of years and discover when our planet was born. Now here's a twist in the story. Earth's oldest rocks, the ones we've found on the surface, are about 4 billion years old. But Earth itself? It's even older. How do scientists know? Because those ancient rocks don't tell the full story. The real clue comes from space, specifically meteorites. Meteorites are like cosmic time capsules, leftovers from the very beginning of our solar system. When scientists date these space rocks using radiometric methods, they consistently find an age of about 4.54 billion years. That number? It's the best estimate we have for the age of Earth and the entire solar system. So in a way, to understand our planet's birthday, we look beyond Earth itself, into the stars and the remnants that fell from them. And the story doesn't end with meteorites. Remember those incredible Apollo missions that took astronauts all the way to the moon? They brought back something priceless, rock samples from our celestial neighbor. Why does moon rock matter? Because the moon itself was born from a colossal cosmic crash. Billions of years ago, a Mars-sized object named Theia slammed into the young Earth. The debris from that cataclysm spun around and eventually formed the moon. So, the moon and Earth share nearly the same birthday. When scientists dated those ancient lunar rocks, guess what? They found them to be around 4.5 billion years old, just like Earth. It's like the moon is Earth's timekeeper, silently holding the secrets of our planet's earliest days. Some of the oldest rocks we've ever found on Earth aren't in far-off galaxies. They're right here, on our own continents. In places like Canada and Australia, scientists have uncovered ancient stones that date back between 4.03 and 4.4 billion years. These rocks aren't the very first to form, but they're close enough to tell an amazing story. Earth's crust, the solid shell we live on, started forming not long after the planet itself came together. It's like finding ancient diary pages that reveal how Earth slowly turned from a fiery ball into the stable world we call home. Hidden deep in Western Australia, scientists found something truly remarkable: tiny zircon crystals, some of the oldest solid materials ever discovered on Earth. These zircons are about 4.4 billion years old, whispering secrets from a time when Earth was just starting to cool down. What's even more exciting? Their age suggests that Earth's crust, and maybe even oceans, existed much earlier than we once believed. It's like these little crystals are time travelers, carrying stories from the dawn of our planet's history. Earth's incredible age isn't just a number. It's the foundation for one of science's most important tools, the geological timescale. By dividing Earth's vast history into eons, eras, periods, and epochs, scientists created a timeline that helps us make sense of everything, from the slow drift of continents to mighty volcanic eruptions, from ancient climates to the rise and fall of life itself. Thanks to this timeline, we can read Earth's story chapter by chapter, understanding how our world has changed over billions of years, and how it shaped the planet we live on today. It's a reminder that Earth's past is deeply connected to our present, and that every rock, ocean, and creature carries a piece of this epic story. Some of the oldest evidence of life on Earth comes from tiny microbial fossils, ancient life forms that lived around 3.5 billion years ago. That means life began not long after Earth's surface cooled down and became stable. It's mind-blowing to think about. Life starting so soon in our planet's history. And it sparks a big question for scientists and dreamers alike. If life could arise quickly here, could it also happen on other planets with the right conditions? This idea fuels the exciting field of astrobiology, where we search the stars for signs that we might not be alone in the universe. Knowing Earth's age does more than just tell us about our planet. It sets a cosmic benchmark. When astronomers look up at the stars, galaxies, and even the entire universe, Earth's 4.5 billion year timeline helps them estimate how old these distant objects are. If they ever found a star or galaxy older than Earth, or even older than the solar system itself, it would shake the very foundations of what we think we know about the cosmos. In that moment, scientists would have to rethink everything, from how stars are born to how the universe began. Earth's age, then, is not just a number. It's a key piece in the grand puzzle of existence. Earth's story isn't just about the distant past, it's also about understanding what's happening right now. By studying climate cycles that stretch back billions of years, scientists can see the bigger picture of how Earth's climate naturally rises and falls. This deep time perspective helps them tell the difference between natural changes and those caused by humans today. And that knowledge? It's crucial. It guides policymakers to make smart, evidence-based decisions that protect our planet's future. In other words, knowing Earth's ancient climate story is key to saving the world we live in. Earth's age, about 4.54 billion years, isn't just a random number. It's the result of careful, ongoing scientific detective work using the best tools and methods humanity has developed. Knowing this number doesn't just satisfy our curiosity about where we come from. It opens the door to understanding the grand story of life's evolution, the complex dance of planets in our solar system, and even the thrilling possibility that life might exist beyond Earth. Science keeps pushing forward, uncovering new mysteries every day. But one thing is clear: Earth's long, rich history is an incredible legacy, one we're still discovering, and one that shapes everything we know about our place in the universe.